properties of inner product. It is the notion of inner product that helps us to take the energy of the signal. For energy signals, so we use inner product definition to take the energy, and there is slight difference in the case of power signals, which are periodic in nature, which we will come across later. So first of all, inner product is defined for a energy signal as, so if x1 of t and x2 of t are energy signals, then the inner product between them is defined as, the symbol is x1 x2 of t in a bracket like this. Okay, this is with corner edges. We denote the inner product using this symbol. So this is a notation. Okay, this is a way we write the inner product, and the definition of the inner product is given as integral t goes from minus infinity to plus infinity first function into complex conjugate of the second function dt. Okay, so first property is called positive definite property. And what is positive definite property? If you take the inner product of a signal with itself, that is x of t, inner product with x of t, we will get by definition, so if you substitute the definition, so we will get x of t into complex conjugate of x of t dt, which is t going from minus infinity to plus infinity x of t modulus square dt. So which is always positive, because modulus is a real valued positive number. After squaring it, we will continue to have it positive. There is no complex part here. So if you integrate out this from minus infinity to plus infinity, all the positive values, so you will definitely going to get 0, and this is also called the energy of the signal. Okay, so you can if you want, you can denote this as Eg or Ex. Let's say Ex, if x of t is the signal, we can call it as Eg, and this energy is always greater than 0. Second property, as I told you, if you interchange the order in which you enter the functions, so if I interchange say x2 of t, x1 of t like this. So instead of writing x1 of t first, I write x2 of t. Then according to the definition, t going from minus infinity to plus infinity. So whatever we enter first, that function in its original form is multiplied with the second entry, which is x1 of t complex conjugate. So this is how it is defined as. Now you can do one thing. You can do a mathematical manipulation from so this conjugate. So what you can do is like you can put a conjugation here and remove the conjugation here. Okay, and then the whole thing, if you conjugate, because the conjugate of the conjugate is the original function, so it is just the same thing. And if you now rearrange this, this is basically integral t going from minus infinity to plus infinity first function, that is x1 of t, into conjugate of the second whole conjugate. So that is basically whatever is in the bracket is basically x1 of t, x2 of t conjugate. So this is Hermitian conjugate property. Okay, so this is, if you change the order, you are taking basically what is called as Hermitian conjugate. Okay, number 3. Number 3 is very important in proving for the proof that we are going to do today. So it has two parts. Say part A. If I have the first function as alpha x1 of t plus beta x2 of t, and the second function, second entry is say y of t, then this is equal to, so I'm just applying the definition directly, minus infinity plus infinity alpha x1 of t plus beta x2 of t into y of t conjugate dt. So this is equal to, I can split it into, I can take alpha outside, and then rest of the thing I can write it as like this, x1 of t conjugate of y of t dt. That is the first term. I can take beta also outside. Beta don't have any conjugation here. T going from minus infinity to plus infinity. x2 of t into conjugate of y of t. And this is basically alpha x1 of t comma y of t plus beta x2 of t comma y of t. In a similar way, you can prove the b part. I'm writing the b part without any proof. That is, if you have x of t, and the second entry, if you have alpha y1 of t plus beta y2 of t, then what you can show is that this is equal to alpha conjugate x of t comma y1 of t plus beta conjugate x of t comma y2 of t. Can you do this yourself? Should I need to discuss this? There will be conjugation because it is appearing with the second part, okay, second entry. So whatever is entering with the second entry, so they need to be conjugated. So I hope you will be able to do this. So these are the three properties that we will use for the derivation that we are going to do now. Alright, so now the problem at hand is to find, so the problem is to find the best approximation of f of t in terms of g of t, as the approximate function is written as c g of t, where both f of t and g of t are complex valued function. Okay, and c is allowed to take complex values. Okay, so let me write that also, and the c is a complex number. So we need to find the best value of the complex number which will best approximate f of t in terms of g of t. So the answer is the best approximation is the one which minimizes the mean square error. Okay, MSE stands for mean square error. Okay, so what is MSE? That is, MSE is equal to the original function difference with the approximate function. So which we call it as FA of t. Inner product with itself, FA of t minus, sorry, f of t minus FA of t. So where f of t minus fa of t is also called as the error function. Error function. So that's the name for the difference. So we want this difference to be minimum, and one measure which we can use is the mean square error, because if mean square error is minimum means the strength of the error function is minimum, or the energy contained in the error function will become the minimum. Okay, so that is equal to, now if I substitute the approximate function as c g of t, c g of t minus f of t minus c g of t. So so I from now onwards I will denote, we will use f and g instead of f of t and g of t, to keep the expressions simple. Okay, otherwise we have to just carry around this p all around. Okay, so that is not really necessary. Later once you derive it, you can put it back always. So therefore your Mse is basically f minus cg, inner product with f minus cg. Now this if you want, I can expand from minus infinity to plus infinity, f minus cg into f minus cg the whole gt, where f and g are functions of time. So this is equal to, you just expand, so that will be f star, that will be the first term, and the second term is minus c f g star, then minus c g f star, then finally plus c star. Okay, that is okay, f star, then minus c g f, this will have c star here. Okay, and c star, g star. Okay, if this looks confusing, you can put it back f of t and g of t and work in that manner also. So this is equal to so f, so for just to avoid confusion, let me just put this back for a moment, only for a short time, and then I will again take it back, just so that you can identify the first function of time and then the second function of time, then okay, minus c integral p of t f of t star dt, going from minus infinity to plus infinity, and then finally plus c star integral t going from minus infinity to plus infinity c of t star of t dt. So this, now I am going to use the concise notation. Okay, so the first term is what? First term is basically ff, that is the first term. Second term is c star, that is fg. Third term is basically c gf, and then so when I write using this notation, this angular bracket notation, then I don't need to put any star there for the second function. Second function is expected to have conjugation in the definition of the inner product. So that is why I am not putting any star there. C star G G. Okay, so it is GG means first function into the second function star. Okay, so So that is, so it's very concise notation, and that is why I prefer like this. Okay, so what comes next? So the way we are going to proceed from here is that we separate out this first term. Okay, this first term, it is independent of C, so that we don't need to bring it into the picture, so we keep it as such. And then from the last three terms, I'm going to take out G, inner product of G with itself, which is basically energy of the signal G of T. So so plus, so let me just take out G star. Oh, sorry, I'm making the mistake if I write G star there. So G I am taking, which is basically the energy. So I am taking this outside. I'm from the three terms. Okay, from the last three terms, I am taking out G. So let me write the last term. Okay, first. So that is C star is what is remaining here. Then I have the next term. I will write this one, C star F comma G divided by, now I have to divide by GG, because I have taken GG. There was no term GG here, so when I take it out, I have to, this is basically a complex number, so you have to imagine that this is basically a real number, right? GG, according to the first postulate, it is a real number. It's a positive number. I'm taking it out. So wherever it is not there, I have to just divide it by it. And then the last term is C. Okay, so yeah, let it be. So G F divided by G comma G. Okay, so it is the same expression. Only thing is that from the last three term, I have taken out G outside. Now the important step here is this. Okay, which is the mathematical trick that I am doing. So the whole purpose is basically to just get rid of this C stars here. So what we can do is like this bracket that we have here, this bracket, this we would like to write as a product of C minus F comma G divided by G comma G. Okay, so this multiplying with conjugate of that is C minus F comma G divided by G comma G. Okay, so I can write like this. Okay, so C minus, it's the same thing in conjugate form. So conjugate of the difference is basically difference of the conjugate. So if I distribute this conjugation, I can put it inside. Okay, so let me just do that. So it will be here as well as here. Okay, now this conjugation of F comma G is basically G comma F. Okay, so if you look at now, when I multiply these, what are the terms that will come out? There will be 4 terms, but I only have 3 terms in the bracket. So I need to subtract whatever additional term that comes out of this expansion. So just let me first expand this, whatever is in this bracket. So let me put a green thing here. So this thing, whatever is in this green bracket, so C star, that is the first term, and then C will be multiplying with minus C F comma G, the whole star is basically G F divided by G G. Then this second term I am going to take and multiply, so that is minus C star F comma G divided by G G. and the last term which is not present here. These three terms are present here. You can see that the first term is this, and then the second term is the last term here, and then the third term is basically the second term here. Added to that, there is one additional term which comes, which is basically f comma g complex conjugate multiplied. So that is this, and then g comma g this one. So this term is actually not there. So what we need to do is that we need to subtract from here that additional term which come out. So then, so that it will look exactly the same as above. Okay. So this green bracket is basically I'm just adding and subtracting this. So let me know if this is clear, this step is clear or not. So these two green brackets, they are same.
Yes, sir.
Okay. All right. So now, so we are here. This previous step.
Sir.
Yeah. Yes. Ask questions.
Can you go just a little bit about the integral expressions that you have written?
Okay. Yes.
Sir, there you have said one thing that about the functions where the conjugate will not be there.
Okay. So what I was telling is that f star tt, no? When I write in angular bracket notation, I will only write ff. The second f will not put conjugate. That is a mistake if you put, because the definition of inner product is such that the first entry, that function, multiply with the conjugate of the second entry. You understand? That's what we started with. The definition of inner product is this: x1 x2 means integral x1 into x2 star. So that's the definition. This is the definition of inner product. So if I write x2 star inside the angular bracket, it means something else.
Oh, okay, yes, sir.
Yeah.
Yes, sir, got it.
So that that is a likely mistake people can make, but be careful that you should not make that mistake. So now, so what we did is we have just mathematically manipulated it. The above step from here to here, this is just a mathematical manipulation. It is exactly the same thing that we get here. After multiplying, we get all the four terms, and so these four terms, out of which the last term which is absent, that is subtracted from this, and then we get only the three terms. So there are four terms here in this multiplication, out of which one term is subtracted, which is the last term. So we have the above step three terms. Okay, so now carefully look at what we have. So let me just copy this. So I'm going to take this to the next page. Okay, so this is what we have. What is this? This is basically the mean square error. We are evaluating the mean square error. So that is mean square error is equal to this. So that is equal to integral f comma f, inner product f comma f plus g comma g, then this bracket. Inside this bracket, what is there? I can write now without any C conjugate. This can be written like this. Now only C is there in this expression. Is it clear? Is it clear to everyone what I did? It's a way of another way of writing. Let me know whether it is clear or not.
Yes, sir.
Okay. Because I am just multiplying one thing, a number with its conjugate, so I will get modulus square. That's what I said. So now what we are interested is find the best value of C that would minimize mean square error. Now if you look at this mean square error, so mean square error is basically containing different terms. The terms are basically one is this term, the other term is G is C minus F comma G divided by G comma G. This is the second term, and the last term is basically so these are the terms. I have three terms in the mean square error. Only one of them is this one is only term that depends on the variable C. This is the only term that depends on C. All the other terms are so no matter what C you take, the first and the last term have no effect on it. So the minimum value of MSC is actually determined by the second term. Therefore, the minimum MSE is determined by the second term. Okay, and what is the second term? This GG is nothing but the energy, which is a positive thing, okay, into C minus FG, inner product of F with G, and divided by G. So it is determined by this term. So sorry, there is a square here. Now this is going to be a positive term. It cannot be a negative term. This is a positive term. So if it is a positive term, what is the smallest value possible? The smallest value of this term. Can anybody tell me what is the smallest value possible for this particular term? This term, what is the smallest value possible? This is the second term here. Anybody? What is the smallest value possible for this term? We have a positive number, and what is the smallest value of the positive number? It cannot be negative because EG is positive. Here EG is positive, and then the square is also positive. Okay. Can anybody tell what is the smallest value possible? Hello, are you listening?
Yes, sir.
Yeah, what is the smallest value possible for this term? EG is positive, and the modulus C minus that modulus square is also positive. So what is the smallest value possible?
The smallest value possible for C.
Not C, for this particular entire term, the second term.
So differential equal to 0.
No, I am asking a very simple question. We have three terms here for this mean square energy. First and the last term doesn't depend on C. Second term only depends on C. So my question is, what is the smallest value possible for this term? the second term. It's a positive number. Second term is a positive number. It will be always positive. No matter what value of C you take, it is going to be positive. So what is the smallest possible value for this term? Because EG, that is G inner product with G, that is giving you the energy of G of T, that is positive. Modulus square is positive. So the entire second term is positive. So what is the smallest value possible for this term? The entire term, what is the smallest value possible? You have a positive number, that second term, which is a positive number. What is the smallest value possible for a positive number? How small a positive number can be? Are you?
And then just greater than 0.
Yes. So smallest value is 0.
Yes, sir.
So by varying C, the best you can achieve is make it 0. That means this term doesn't contribute. So the smallest value of this term is 0. You can't go below that, right? Because it is a positive. And when will it become 0? For what value of C it becomes 0? So you don't need to even to differentiate this. It is a very common sense way you can find the answer. That is when C is equal to
F1G
Fg divided by Gg.
GG. Yes, sir.
So that is the result. That's all. So we get the best value of C when we have C taken as F inner product with G divided by the energy of the signal G. Okay, so what are we saying? So we have completed the derivation. We got the value of C. What we are saying is that the minimum mean square error, or the best value of C that we can take, is multiply the function G with a constant where C is equal to F inner product with G divided by energy of the signal. Okay, so therefore the best approximation is Fa of t is equal to C, which is divided by Eg into G of t. So this constant is what we have found out. This is just a constant multiplying G. Okay, it's a complex number. Okay, so we found the best complex number that you can take is F inner product G divided by Eg. Is it clear to everybody?
Sir.
Okay. Now I'm going to extend this result further. So before that, I'm going to introduce what is called as orthogonal. Let me use a orthogonal set of functions. So I'm going to consider a set of functions which are having some special character, and let me just write down their property. So G1 of t, G of t, G2 of t. Earlier we have only one G of t. Now I am telling that I have n number of such functions. G1, G2, G3, etc. say up to G capital N of t. I can have infinite number of such functions also. Forms are forms a complex valued orthogonal set of functions, or in bracket we are talking about signals, if inner product of gi with gj is equal to, let me write like this, 1 if I is equal to j, 0 if I not equal to j. Everybody able to understand this? I have n functions or n signals. They form some kind of set. They have a property, that is, if I take inner product of any two functions from this set, if the functions are same, I will get I will get basically energy of let me write like this, energy of that function, otherwise I get 0. That means if I take g1 with g1, I will get e1. If I take g2 with g2, I will get energy of that, etc. But if I take g1 and g2, I get 0. g3 and g5, I get 0, etc. So a set of functions which satisfies this property are called orthogonal set of functions. If you take inner product with itself, you get the energy of the function, but if you take inner product with any other function in the set, you get 0. And this you can write in a shorthand notation. You can write like delta ij into ei. This means just whatever I have written with this in this bracket, whatever I have written, this is a short way of representing the same idea. If I delta ij equal to 1, if I equal to j, it is equal to 0 if I not equal to j. Okay, so where delta ij is called Kronecker, this is not Dirac delta, this is Kronecker delta. Dirac delta is delta of t, this is delta ij. Okay, so this is equal to 1 if I equal to j, 0 if I not equal to j. Is it clear to everyone, the property of orthogonal set of functions?
Yes, sir.
Okay. So we are going to repeat the previous derivation with respect to complex valued functions, but now not just going to express in terms of one function, but in terms of every function in the orthogonal set. Okay, so question is this now: approximate f of t in terms of all the functions in an orthogonal set. That is, the set is again g1 of t, g2 of t, etc. up to g capital N, that is the last entry. And we will see later that this capital N can be infinity also. You can always find set which has infinite number of functions that forms an orthogonal set. It is possible to make. So approximate f of t in terms of all the functions in the orthogonal set, okay, such that Mse is the minimum. Okay, so that is how we are going to do it. So let me write the approximation. Fa of t, the approximate signal, I am going to now write Ci Gi of t, where I goes from 1 to n. Earlier there was only one function, so we had one constant. Now we have n function and there are n constant in the approximation. So the error function the error function. E of t is what? It is f of t minus f a of t. That is f of t minus sigma ci gi of t. I is from 1 to n. So again, note that ci is a complex number. Okay, and this orthogonal set is also complex valued function. F of t is also complex valued function. All are complex valued. So this is just an extension of the previous result. The derivation is exactly the same, but it is good to repeat so that you will get used to it. So what is Mse? Mse is inner product of E of t with E of t. So I will drop this t here. I will write it as f minus sigma I ci gi. Okay, I will write only gi. This is the first entry, and the second entry is also the same because I am taking the strength of the error function. So second entry is also the same. So far, is it okay, everyone, with me?
Yes, sir.
Okay. So now let's just expand as before. Now there is a important thing that we need to keep in mind. The first entry I am using a summing variable. Second entry also I am using a summing variable. So one question to you, can I have a different variable here from the second place? In other words, can this i's vary independently in the first position and the second position? Is that allowed? That means what I am asking is, can I have j here? Will there be any problem if I put j here and ci here for the summing variable? I and j are summing variable. The question is, which is more appropriate? Taking I on both entry, or I on first entry and j on second entry? I am writing E of t in both places. Okay. So I would prefer to take I in the first entry and j in the second entry because there are n terms here in this summation and there are n terms here. So when I take the first term, say I is equal to 1, but when I is equal to 1, j can be anything from 1 to n. But if I use I here also, if I take 1 here, I should take 1 there also. So in order to avoid that confusion, to make it very clear that I can have any value for j here when I is taking a particular value. So that is why I am using a different variable for summation. Is that clear?
Sir.
Yeah.
So, but that variable is for I that you have written from I equals to 1 to n.
Yes,
and so
this
here
is just a
j
variable. I can write like this also, right? I can write f of t minus sigma j going from 1 to n. It is it's just a variable of summing up.
Okay, sir.
Does the result depend on what variable I use?
No, sir.
No. I just need to sum up all the cases. So to denote each case, I am using a variable. So it's just a dummy variable, just for keeping track of the terms.
Yes, sir.
But what I am saying is that when you take E of t, inner product with E of t, and there are n terms here and n terms there in the summation. So in order to keep the freedom of the second entry, which doesn't depend on the first entry, to keep that freedom, I am using a different variable here. Is that clear?
Yes, sir.
Okay. So just like before, I will have ff, that is the first term, and then let me write like this, minus f comma sigma j cj gj. This is the second term, so that is what I am doing. I am taking first inner product and distributing this with this, and after that I am distributing with this. Then I will distribute this, and this is the next two terms. So that is minus sigma I going from 1 to n gi, then comma f, then final term is minus minus plus sigma I ci gi, comma sigma j cj gj. Just like previous case, except here we have sigma, and therefore the second and third term has basically n inner products there. We can expand it as n inner product using the property of inner products that we have discussed in the first part of the class. And the last term has basically n square terms, n square inner product. Is that clear to you? The second and third term has n inner products each, for each value of j and each value of I. And the last term here has n square, capital N square inner product. So j is varying from 1 to n, I is varying from 1 to n. Is it clear?
Yes, sir.
Yeah. So let's just write in such a manner that I will take this constant and the summation outside the inner product. This I can do by using the sesquiu linear property. You remember the sesquiu linear property which we saw first today in the class. One of them I have proved. So this is the sesquiu linear property. Okay, sesquiu linear property. So if the summation is on the second part, then I will have complex conjugate on the constants when I pull it out. I can write it. If the summation is on the first part, then when I pull out the constant, there will be no conjugation. That is the difference. So you have to see where is the summation, and accordingly you have to put conjugation or not. So first term as such, no difference. The second term, so I am taking the summation outside, because integral of the sum is basically sum of the integral. Okay, inner product operation is an integration, and we are integrating over many sum of the products, and I am taking out all the integration separately, so we will get sum of the inner products. So first of all, sigma j is from 1 to n. Now when I pull out the constant, what will be whether there will be conjugation or not? Can you say? According to sesquiu linear property, the summation is on the second entry, so the constant here Cj, when I take it outside the inner product, what will happen?
Conjugate.
There will be conjugate. So Cj f gj. Okay, so I can write like this. So sum of the integral is integral of the sum is inner product of sum, so that is integral of the sum, and that we are writing it as sum of the integrals. Okay, and the coefficient here will have conjugation, because when you take it outside the integral, because of the conjugation of the second entry. The constant is coming in the second entry, so when you take it out, there will be conjugation. Then minus, here also we will do like this. So here it is I going from 1 to n, and I will take the coefficient here also outside, but this is in the first entry, so it will be Ci Gi comma F. Now here there are n square term, I going from 1 to n, j going from 1 to n, there are n square term. So I can take both summation outside. You can write it as sum of n square terms integrals. Okay, so I going from 1 to n, j going from 1 to n, and they are independent variables. So and wherever it is first entry, I will not have conjugation. Wherever it is second entry, I will have conjugation. The shorthand notation is a very powerful tool. So here it is J. Is that clear?
Yes, sir.
Okay. So now we are almost there. But one observation. The second and third term, we have a summation. Now whatever, so there are n terms here, n terms here, so I can combine these two terms. So this is f comma f minus sigma. I can use I only to write both terms, just like I did earlier. I changed it into different variable. Now I am changing back. Okay, so the first term is Cj star f gj, sorry, I am using I, so I have to be careful. Okay, so I am using I instead of j, so it will be Ci star, then f gi. Okay, that is the first entry, and then I am using the same summation variable for the second term also, sorry, third term also, where I have plus Ci, now star here, and this I am going to interchange and write it as f comma gi conjugate. I can do that. Now the interesting thing is that I can also bring in okay, so that I will do it as a second step. Okay, I will do one more step. Now you look at this inner product of gi with gj. I told you about the property of orthogonal set. Gi gj, that is equal to delta ij ei. It is equal to delta ij ei. That means when I and j are different, it's 0. That's the property of orthogonal set. So only non-vanishing terms out of the n square term, most of the terms are 0. Only the diagonal terms, that is when I equal to j, that is the only term that is going to survive. So I can write I going from 1 to n, Ci, and that time j is equal to I. So I can write that also with the same variable, Ci star, and the value is going to be Eg. Is that clear? That will be the last step. There are n square terms. Whenever I is not equal to j, those inner products are 0, so those terms will vanish. But only term that doesn't vanish is when I is equal to j. If I is equal to j, I can replace j with I, and in that case it is the energy of g of t. So I write it as Eg. Now I can combine the last term with the previous two terms. Is it clear so far?
Sir.
Yes.
Sir, did you took here I equals to z for gi and gj?
No. There are n square term. I can vary independently without j
Yes, sir.
from 1 to n, and j can vary independently from I from 1 to n. But the point is that gi inner product with gj when I not equal to j is going to be 0.
Hmm. Yes, sir.
Since they are 0, I will not get any contribution from there to sum up. How many contribution I will get? Only the cases where I equal to j. How many such cases are there? Out of n square cases, there are only n cases which will survive.
Hmm. Yes, sir.
That is the case where I equal to j. And if
I
it
agree.
is only I equal to j, I am putting j equal to I here. And this inner product will become Eg, energy of the g of t signal.
Sir, is it the energy of error signal?
Energy of the signal okay, I think okay, I have to improve this. This is a confusion, maybe it should be ei, energy of the ith function, that is gi, energy of gi in the orthogonal set.
Yes, sir.
Yeah, I think if I write eg it is not clear, so I should write ei. Okay, gi inner product with gi, we will get ei, energy of that signal, and there are n different values I can take, and therefore there are n terms here. So now I can combine all these terms under one sigma. So this is equal to f comma f minus, like before, I would like to take this ei outside. So sigma I going from 1 to n, let me take ci star f comma gi plus, I am dividing it with ei and taking out my ei outside, and then ci, here it is f comma gi conjugate by ei, then final term is going to be ci star. So I have taken out ei outside. Now I am going to do the same mathematical trick which I did earlier. That is, I am going to get rid of this complex coefficients ci star by carefully writing whatever is in the bracket as. So I will write whatever is in the bracket as modulus ci minus f comma gi by ei square, and there is a fourth term which I need to subtract, which is a square of this, f comma gi modulus square by ei square. Okay, so this is multiplying ei. Is it clear? I dropped some of the steps here because we have already seen that from the previous problem. So this modulus square is basically this term in the bracket or in the inside the modulus into the conjugate of that. I will generate 4 terms. Out of that, the last term is not present here. All the other 3 terms are present. So I need to subtract away that term.
Yes, sir.
Yeah. So now the question is, again, it is the same question what was asked before. So let me, before I ask that question, so let me write it like separately now. So this term is EI into modulus CI minus F comma GI divided by EI the whole square, and minus minus plus. So this is I think somewhere I made a sign mistake. There is a sign mistake. Yeah, there's a sign mistake is there. So let me correct it. It has to be plus, and all the signs should go inside. Okay, so up to here it is correct. Now here I am going to put this plus here, which means that I'll have a minus here, and there will be a minus here. Okay, minus here, so those two minuses I am putting it back, and the last term is plus. Again, this is plus, and okay, so this is also minus. There is a minus sign here, so I am keeping the minus here with these two terms. So, okay, then only this is equal to this. This becomes equal to only if I keep this minus, because there is a minus sign here. So when I multiply, these two terms will be minus, this will be plus, and the last term which comes out of this expansion is plus. So I am subtracting this, so there will be minus. Okay, so therefore this is plus. Okay, now I have rectified it. F comma GI whole square by EI. So these are the this is the final expression. Okay, so there are three terms. The second term, that is this term, is the only term that depends on the constant Ci. So the question is again, what is the best constants C1, C2, C3 I should take so that we can have a minimum value for this MSE. This is MSE. So therefore MSE is minimum when Ci is equal to F comma GI divided by EI. Why? Because it will be 0. There are n terms here, but each term will be individually 0 if I take each constant like this. So each constant is found out how F inner product with that particular function in the orthogonal set divided by energy of that particular function in the orthogonal set. So let me write, EI is basically GI. So ask questions if you have any. Is it clear? It's the same derivation. Only thing is that we have done it with respect to a set of functions instead of just one function. We have approximated f of t using many functions. Now you can think about it like the components of a vector ijk, they are orthogonal. Okay, if you have a vector, like this, okay, in a plane, and two unit vectors or two vectors are given. One is in say I cap, other is j cap, and they are orthogonal. How do I say? I dot j is equal to 0. So they are orthogonal. So there are two vectors in the set. One is I cap, other is j cap, and they are orthogonal to each other. And I dot I is what? I dot I is 1, j dot j is also 1. So they have unit length. So this is like your E1 and E2, both are 1. Now what we are saying, what should be the best constant I should multiply with I, so that I will approximate the given function in terms of I and j, which are unit vectors. So the best possibility is increase the length of this I till here, increase the length of j till here, and then when you add these two functions, you will get a exactly. So the question is, what is the best coefficient? So that is ax. According to our rule, it is the given function, okay, inner product. So in the case of vector, we will use dot product, not inner product. So that is ax is basically vector a. So f inner product is gi is like a dot with I divided by the length of, that is I, this one, okay, but I should use dot product, I dot I. Okay, so but denominator is 1, I dot I is 1, a dot I is basically ax. So we have re-derived this for the case of function by using the concept of inner product. So, is it clear?
Sir,
Yeah.
sir, can you please explain once more interpretation? That part, sir.
So basically we have a vector A which we want to write in terms of I and j. So I and j forms an orthogonal set of vectors. Why? Because I dot j is 0, I dot I is 1, j dot j is also 1. So this form an orthogonal set. So if an orthogonal set is given according to this formula, that is Ci equal to f comma j gi divided by ei. Okay, I am applying the same formula. So this vector which I have here, if I want to find out what should be the best constant, I should multiply with I. So my purpose is basically to write a, the vector a, as some constant ax into I cap plus some another constants ay into j cap. This is my intention. So I don't know which constant is the best one to take. So what we found out is a formula to find the best constant. So the best constant is given by these formulas. That is, if you convert inner product to dot product, you can talk about the same thing in the vectors. Vector a dot I divided by energy of, or the energy means here it is length square of I, that is corresponding to ei is basically inner product of gi with gi, right? So similarly inner product of I with I, or dot product of I with I. So similarly ay.
Yes, sir.
Yeah. So it's the same thing what we are used to. Vectors are expressed. This is called decomposition of a vector. Any vector in a space can be decomposed into its components ijk, where ijk form a orthogonal set of vectors, but we have extended that idea to the world of functions. Okay, so where we have instead of a dot product, we are using a notion of inner product, and we are so far discussing with respect to energy signal, and in the next class I will tell you how to extend the idea to power signal, and then I will also show you the derivation of Fourier series. Okay, Fourier series comes out of it. Not only Fourier series, all the orthogonal set expansion come out of it. So that is for the next class. So I'll stop here. If you have any more question, you can ask.
Sir.
Yeah.
But then all these orthogonal set of vectors only comes out of Fourier series. It's like
it's not just Fourier series. Even what we did earlier, expressing a given signal in terms of impulse functions, Dirac delta functions. You remember?
yes, sir.
We had a formula. If you remember, so let me rewrite that formula here. I said that f of t can be written as in the continuous time domain. I can do it like this, as an integral tau going from minus infinity to plus infinity. F of tau into delta of t minus tau d tau. So this we have derived earlier. Okay, so this can be looked at. So given function, we are expanding in terms of an orthogonal set of function. Here the orthogonal set is consisting of Dirac delta function, which is shifted by d tau unit from minus infinity to plus infinity. So there are infinite number of functions here. Okay, so
Yes, sir.
Laplace transform is also a special case of this. Fourier transform is also a special case of this. Fourier series is also a special case of this. So everything that you study in this course is actually a, you can say it is a branch of this one way or the other. So we are basically in the study of signals interested in expressing a given signal in terms of standard signals. Standard signals whose response of the system can be easily understood or found out. So if you express a given signal in terms of standard signal whose response can be easily found out, we can find the response of the system to any signal. Okay, when we express it in terms of impulse response, we know how the system behaves with, if we know how the system behaves with impulse response, then we know the output of the system. We said that it is equal to y of t is equal to h of t convolution f of t. So f of t is expressed in terms of impulses, and I know how system will behave with respect to impulse input. So therefore my response to f of t is basically a convolution of f of t and g of t, f of t and h of t. So it's the same idea. I know how the system behave with impulse, but I don't know in general how it will behave with respect to other signal. But all you need to know is impulse response. That's what we are saying. We will express the given signal in terms of impulse. If you know how the system behaves with respect to impulse, then you can find out easily how it will behave with any arbitrary signal, because we can express any arbitrary signal in terms of impulse using this formula.
Yes, sir.
Yeah.